The most rewarding part of being an ADIA Lab Senior Fellow is really the excellent opportunities for networking and the environment for networking that ADIA Lab creates, especially during the yearly symposia, but also during various seminars that the laboratory is running across throughout the year. And I have made contact with top scientists in different fields: health sciences, climate sciences, statistics, mathematics, and computational sciences. Like, I'm a computational scientist myself. And the idea here is really to bring together these top scientists, many of those Turing Award winners or Nobel Prize winners, and create an environment where we can design new ideas, ideate new things, and really launch bigger projects, such as the climate project I was talking about earlier. I think the single key insight I want the audience to take away is that we just recently really discovered a way to achieve a form of intelligence that is very competitive with humans, certainly very competitive with myself. And the key idea behind this is actually relatively simple. So the first part of the idea is that we have been scaling these language models for the last couple of years. So in my talk, I will talk about how we scaled them beginning from 2017 to basically today, with larger models, more data, and we created entities that are extremely comprehensive knowledge databases. Better than any human, better than any group of humans, I would even claim, in retrieving facts. But then when you interact with these models, they're kind of not super smart. So they can give you a lot of facts. They know the capital of, I don't know, strange country. But what they don't know is they cannot reason. But what happened a couple of months ago is that these models, which are called large language models, and the talk's called From Large Language Models to Reasoning Language Models, that they have been amended with the capability to reason. So how did we get to the capability to reason? Well, we actually, in the talk, I go back to 2016, where for the first time, a computer beat the best human player of a game called Go. And many of us know that game, especially the Asian colleagues. And that game is extremely simple to explain. The rules can be explained to a young child, but it is extremely strategic to play. And the strategy is encoded in another deep neural network. It's actually encoded in a very small deep neural network. And that beat the best human at the time, Elise et al., in a very impressive show, I would even say. It was internationally televised, and I recommend everybody to watch that documentary. There's a documentary online of exactly that. And we take those together. So we now take the language model, which is the superhuman knowledge database, and we take the reasoning capability of some algorithm very similar to AlphaZero or AlphaGo at the time that beat the best human, as a reasoning component, and we put those two together. So we have a superhuman knowledge database and a superhuman reasoner, planner, and now obviously what comes out of it, because these are the two aspects to human intelligence, maybe a superhuman intelligence. I'm not saying that we are there yet, but I see a path going forward. The only limitation we have today to that path is the cost of our compute resources. So we know exactly how to go, it's just too expensive to do so. These are the two sectors that ADIA Lab focuses on specifically, and I'm happy to help, and they will have a profound impact. In fact, there is a study that was published end of last year where a very eminent group of clinical researchers, so doctors in the United States from MIT and Boston, were actually looking at the performance of O1 Preview, which is the first reasoning model in widespread adoption that was released by OpenAI at the end of last year. So it was a preview model. The performance compared to human doctors. So they set up a committee, and they were actually giving humans tasks. So, for example, you get the following diagnosis, or you have to create a diagnosis based on certain inputs, or you have to determine what are the next tests to be performed on the human subject to figure out what the actual disease is to get to a better treatment. So they were posing these questions in written form to human doctors, and to the AI model, the O1 preview. And it turned out that in that particular paper, in that particular setting, the committee that later graded the questions was actually preferring the answers of the AI model in most of the cases, so about 70%. Depends on the set of questions. I would recommend you to read this yourself if you really care about the details, but that was very shocking. So already today, these reasoning language models, and it's really about the reasoning model. These standard models, they couldn't do that. But the reasoning models who give you an explanation, who think like humans, who have thinking steps and so-called thoughts, they enable solving these very complex problems, and especially in healthcare, especially when you have to reason about very complex settings. So these questions that they asked, they were not simple. They were actually very hard questions, because the simple questions anybody can solve. But if you go to questions that are not so obvious, then you can actually have the language model win. And it's not a competition. I don't want to pose it as a competition. I would love my doctor to be amended by a language model, to use the language model. Because what we can say about the language model is it has read all the hundreds of thousands, millions of publications in a public medical database that's called PubMed. This is where all the medical research is published. No single human has read all of that database, just as knowledge is in no single human's head. So it's not the doctor's fault that the model is better. So the doctor needs to understand how to use these models. And there will be a very quick, very sudden impact in countries that allow using those models. Now we could talk about regulation and things. I mean, I'm not an expert here, but if this becomes possible, this is an absolute breakthrough in healthcare, in treatments, and in many other things. And those are just the text-based models. I'm not even talking about the image-based models. Now, you also asked about sustainability in the sense of climate, which is the second key focus area of ADIA Lab. So in the climate area, this could have an even larger impact, because right now our major limitation in predicting the climate is that the resolution at which we are computing the climate is not sufficient. So what does that mean? What does resolution mean? So we have the planet Earth, which is where we live on, and now we want to predict what is the weather over Abu Dhabi, or the expected weather in 100 years from now. So next generation, or maybe next 2 generations. So how do we do this? Well, we don't know, because 100 years from now, everything will be very different. But what we can do is we can take the weather forecast, which we are pretty good at, actually predicting the weather for the next 7 days, maybe 2 weeks, we're extremely accurate. And we can now take these similar equations, which are Navier-Stokes or Eulerian equations that basically simulate the atmospheric state. We can run the simulation forward with a bias, for example, with growing CO2 concentration in the atmosphere. So we could run the same simulation and change the CO2 configuration, which is what the IPCC is doing in these simulations. But now the problem is, we are running weather forecast on extremely large compute resources today. So in fact, we are running a weather forecast for the next 7 days on some of our largest computers. So now, if I want to run this for 100 years, not 7 days, well, that's obviously infeasible if I already need the largest computer for the next 7 days. So what do we do for the climate time frame? We reduce the resolution. And what does that mean? It's like a picture. I'm taking a photo of this room or of the city, and now the photo has so many pixels. And the more pixels, the more detail of the city I can represent. Now, when we run weather forecasting, for example, in Switzerland, we run at a 1 kilometer or 500 meter resolution, which means every 500 meters over the country, there is a grid point that represents the temperature, the humidity, the wind speed, and all of those variables. So now when we do this, and this is for the 7-day forecast, right? Massive compute resources, just for Switzerland. Switzerland is tiny. So if we do this now for 100 years, what we typically do is we coarsen the resolution to something like 25 or 50 kilometers. So that's a large factor, larger. So now we would only have a handful or maybe a couple of handful of grid points for big cities or even whole countries, which is of course not a faithful representation. At a 25 or 50 kilometer resolution, we don't even naturally see clouds form. So we have to somehow parameterize these clouds. So we have to make them artificially form based on physical explanations. So as we increase the resolution, the accuracy will go higher. So today, we cannot afford to run a 100-year climate simulation at a very high resolution because it's too expensive. So we run this at a low resolution. That means now it's not very accurate. So how do we get to the full accuracy? Well, there are now two ways, as I mentioned earlier. One way is to accelerate, or in other words, make the simulation cheaper. So we can increase the resolution to a 1 kilometer global resolution, for example, or 2 kilometers global. By the way, the Earth has 511 million square kilometers. So that's at a 1 kilometer resolution, that's going to be 511 million points for every variable on this planet. So that's a lot. And we have many variables. We have many pressure levels in the atmosphere. So that's hundreds of variables actually and pressure levels. So times the 511 million. And so now what we do is we make this faster. The other way is we could try to employ the AI models that we are developing, now very different from language models, by the way. Because these AI models, they don't deal with language input. They don't talk to you. But what they do is they produce images, essentially, of the atmospheric state. So they're called fields. I mean, they can be visualized as images. They are not images like the city image. The variables, the temperature at each of those, for example, 511 million grid points, the humidity and the pressure, and then they forecast those. It has been shown that for weather forecasting, I can use these AI models at exactly the same or even higher accuracy than the simulation, but about 1,000 times cheaper. Now we have 1,000 times again. 1,000 times cheaper is a very large number. So now if I get this 1,000 times cheaper, I could actually run this over decadal periods globally on the Earth. Because climate we need to run globally, by the way. Because for an air particle to travel around the Earth in the higher jet stream, in the high speed jet stream, that's about 7 days. So 7 days, our climate is basically globalized in some sense. So if we want to simulate 100 years, we must run globally. We cannot just run Abu Dhabi. And so this is why we need this extreme compute power, either with very high accelerated classical simulations or replaced by AI models. Both are viable options. If you ask me, in the near future, we will be using a hybrid of the two. Because if we have a really strong understanding of the underlying physics, it would be silly to throw this away and to learn this with a data-driven model. It may be possible, but it still seems kind of silly. However, there are some things that we just don't know, don't model in the model. For example, the existence of that high-rise here, or the high-rise we are sitting in. It's most likely not captured in the model. However, it has an impact on the climate state, and it thus has an impact on the climate simulation, and we can learn this from the data automatically, the existence of all the different forests, of all the different cityscapes, of all the different landscapes, and the exact topology. So these are all opportunities to combine AI with classical simulations to move this field, this sustainability prediction of climate risks, of climate development forward big time, using AI, of course. That lowered the compute resource cost, and that now makes it possible to jump forward. And in my group, as I mentioned, we've also contributed to this with various collaborators, with making it 1,000 times faster. DeepSeek had another speed improvement, but it's really all about optimization. It's really all about the availability of compute performance, but also the affordability of compute performance at the same time, because we have limited resources on the planet. Goes back to the climate field, right? So we don't want to waste all of our CO2 budget on AI models. We really want to make them cheap and sustainable to run. So DeepSeek was indeed a significant step forward. They actually managed to train a model that is competitive with the big players' models at a rather low budget. And just this fundamental message, and I'll also address this in my talk today, this fundamental message created hope that now smaller players, like smaller companies, or even research labs, could get to top-class AI. Because before this group showed this result, training a model that is competitive with GPT-4o at a budget of about $5.6 million, everybody thought that this was impossible. Everybody thought that you needed billions of dollars, like the endowment of OpenAI, to create these models. And now it is clear, oh well, it is clear, it is claimed that you can do it that cheaply. So it's much easier to get something like $10 million to get the company started than it is to get $10 billion to get a company started, or even $1 billion. So now this creates hope. I personally believe, actually, Jevons paradox is going to hit us very soon, because now that these models are more approachable, they will be used more. I will run this model in my talk on my laptop live. It was unthinkable 2 years ago that you can run such a capable model on your laptop. My laptop doesn't even have a capable GPU. It runs this model. Now this means that if everybody runs this, there's a huge market for hardware innovation to run it quickly or fast on your cell phone. So this will actually create even more value. So Jevons paradox really says, if I make a resource cheaper, I will not reduce the use of that resource. I will indeed create more demand, which will probably lead to more use of that resource and not less use because it's cheaper. And that has happened many, many, many times in history. Basically every single time you build a faster computer, people figure out how to use that speed. It has never happened that we built a faster computer and people said, oh, that's too fast, I don't need it. Right? So many times the software just got less efficient because they could afford it, they could employ better or quicker software engineering methods. But now in AI, if we have these breakthroughs, they will just amplify the demand, they will amplify the use, this will be great. The other thing that happened, actually, is that this company released the model to the public. You can use it. You can use it on your cell phone for free, absolutely free, under your full control. You don't need to entrust your data to some cloud provider that you don't know who that is. You don't know who sees your data. The only thing you know is that once your data goes in there, it will forever be there, that it's not deleted. That's probably the thing you know. But now you can run it locally on your laptop. You have full control. You know exactly what you're sharing. Nothing, if you don't want to. And that's a great step for democratization of these AI methods. The other impact of this model is, it's free, it's private, and it is documented how they trained it. But the more important aspect of this is now that it's documented how to repeat it. So research labs like mine, research groups like mine, can now go and build on this and move things forward. That is true openness. That is true sharing. And this is quite nice. So this will have a major impact. It's a major leap forward in many different ways. ADIA Lab creates this environment where people like me flourish. So we talk to other interested people. I got the opportunity to talk to health people. This is why I'm now looking at health data and applying LLMs to health. This is developing new interests. I just had a wonderful conversation with a colleague here about genome analysis and genome learning, or genome AI in this sense. This is the first impact, also the climate aspect of it. This is great. So it creates connections between fields that may otherwise be disconnected and exist in silos. Then Abu Dhabi specifically, or the UAE, can also play a very important role as a local hub for technology. I mean, in this sense, there's a huge similarity between countries like Switzerland, where I'm coming from, and UAE. Because both of these countries are somehow have a special standing in their vicinity. I mean, primarily I've been involved as a speaker. So I've been speaking twice. So my first talk was on accelerating traditional climate simulations. So how do we get towards kilometer scale global simulations, as I described earlier? So we had a 10-year roadmap basically to get there, and now we're well into this roadmap. We actually have a lot of successes in this area that I'm very proud of, so that's going great. Last year, I was actually talking about now the second prong in this work, where how do we replace parts of the climate models with AI methods, directly data-driven models, data-driven learned models. And here I was actually striking a balance between saying what is possible, but also what are the pitfalls. Because in these AI methods, these models are great at cheating. They're wonderful at cheating. Because what you do with these models, how you train them, is you give them a loss function. You tell them to optimize a certain computational structure, and you define a value function. So this is like, I give you money if you solve the following problem. And I give you a very specific set of rules that how you make money with this problem. And now these AI models are extremely good in exploiting unintended holes in those rules. So it's extremely important to build the right loss function. We are not very good in building the right loss function because it's very task specific. So now these models cheat. So what I've shown in the last talk, for example, is that the models perform extremely well for everything they're trained with. So they're trained to predict the average temperature or the wind speed in X and Y direction. So that's part of their training, part of their loss function. But now a very important aspect is the vertical wind speed. There's actually a lot of damage in ports, in big ports, like Singapore, for example, where you stack containers very high. If the vertical wind speed is too high, they begin to vibrate and they can topple over. So it's like very often hundreds of thousands of dollars damage. So you're interested in vertical wind speed. These models have not been trained with vertical wind speed. And they have I show in that talk that they have an extremely bad representation of vertical wind speed. By the way, referencing to past talks is always nice. All of those talks you can find on YouTube and watch them again if you're interested in the details of this. So what I'm looking most forward in this healthcare area is actually to look at the right tokenization, to look at the right representation of data. Now, that process is very specific. We know how to do it for language. Like, so for example, in English, we take a word like going, and it's most likely represented by two tokens, go and ing, because ing is very common. It's a very common ending of a specific grammar construct in English, and go is the base word, so to say. So now that works well for language. We understand how this works for language. We have some first results how this works for climate fields. But now, how does this work with the human body? For example, DEXA scans and CT images of the body, how do we tokenize those? How do we tokenize musculoskeletal structures in the bodies? How do we tokenize my joints that are sometimes hurting when I sit in planes for too long? So these are things that are extremely important and still open problems. And I would love to tackle those and really to understand how to represent the human body or parts of the human body in the internal representation of an AI model. Get your hands dirty. That's my major advice. So I'm a systems person. So I started with building my own computer when I was in my teenage years. Actually, I was building my own cluster computer with a system called MOSIX at the time. So my mother really hated this because under my bed I had basically a whole lot of trash computers that I found somewhere that people threw away, but I built my cluster out of those. And now I'm building supercomputers, partially the largest machines on the planet. And this really, start early. Start as early as you can and get your hands dirty. Like, build these systems, run your own AI models. Like, if you're alive today, for example, one thing to do is to make sure to run these new models. Make sure to run DeepSeek yourself on your laptop, on your machine. Understand how it works and try to optimize it, try to make it faster. Because that is the major impact that you can have today. As I mentioned, it's all about the computation. So much of the field is driven by making these computations more affordable and cheaper in some sense, with various ways, data science optimizations, but also architectural optimizations. And today, in order to have most success, you need to be an expert in the data science aspects. So you need to understand what tokenization is. You need to understand how these models represent the option space, the reasoning space. Today we're talking about reasoning models, which many people actually don't, and there's a lot of research to be done to understand this. In my group, we do a lot of research trying to understand what these reasoning models actually do, because we see their work, but we don't really know how they work internally. For example, when is a reasoning step finished? What does it mean? Can we identify thoughts in the output of the model? What is a thought? It's very hard to even define for a human what a thought is, if you think about it. Is it a set of, in your head, right? Is it a set of words? Is it some abstract representation of the problem you're thinking about? It's probably a mix of the two. These language models also have the mix. They have an internal state, the activations, the vectors they work with, and then they have the words that they utter, that they output on the screen in the detokenization process. So it's the data science side. The other side is building systems. So you have to be an expert in both. Building systems that perform these computations fast. So one part of my talk today will actually be an effort, an international effort, to build a new interconnection network for data centers to drive AI workloads. This is called Ultra Ethernet. It's a very systemsy approach. So you basically build a network to connect machines, to build supercomputers, or to connect accelerators, to build very large supercomputers, to train these AI models. This network is optimized for these specific workloads. So you need to have expertise in data science, in AI, in order to design such a network the right way. But you also need to have expertise to design the network in order to run a large-scale AI supercomputer, because otherwise you wouldn't be able to do so. So I would really recommend to focus on the intersection of the two, because that creates a unique skill set that you could use moving forward into this brave new world.